So talk about the continuity. So I want to talk about, so everything we talk about in math class should be commonsensical. It should be intuitively clear. But if you say something intuitively, so it's different thing that you say something intuitively and something is intuitively clear. They are different things. I want to be intuitively clear, but we want to say that thing in a completely rigorous way. So let's think about continuity of the single variable function. So for example, everyone knows that this function, let's say y equals to x equals to square, where the domain is 0 to 1, let's say 1, 0. So here's endpoint. We know that this graph is continuous, and therefore the function is continuous everywhere. How do you know it? How do you prove it? What do you mean by that? So what do you mean? So our question, what do we mean by y equals to x squared is continuous? Just think naively. How do you explain it to your nephew who is just entered in the primary school? Something is continuous. How do you explain it? I mean, not even the nephew. Let's say you have a cousin who is high school student who just entered the high school. It just started to learn about continuity in high school. How do you, and he asks, what is about continuity? I don't understand the continuity. How would you explain that? How would you explain that? Well, let me call the names. Okay. 도한수? 도한수? Yes. How would you explain continuity? Oh, it's not breaking. Okay. So I'll give it time to discuss about this continuity with your group member. Okay. So have a little bit of discussion about how to describe continuity, and then let's get back again. So I'll give about 2 or 3 minutes to discuss within your group. So just share your ideas. Have a discussion. 조용진? 8. Wait. 조용준, 권혁빈. Your group is, wait. Your group is 8, and you're doing project 5. Project 5. All right, so group 4, Kim Yun-seo. Okay, group 4, Yun-seo. So what do we mean? What do we mean by continuity of a function? How do you explain it? So the value exists. And what? And what? I can't hear. Okay, left limit and right limit. Okay, so left limit, right limit, and they are the same. Okay, good. So another one. Anyone else? How about group 6? So I did. So group 2, 심지원. 심지원? Yes. What did you discuss? Okay. Equals to what? FA is equal. Okay. All right. So good. How about, I'm just saying that I'm saying good, not because you had an answer, just because it's a good way of thinking. I mean, right way of thinking. Hong Sun-min, group 10. Yeah. So how did you discuss? Okay. It's the same idea in the first one. Okay. So anyone else have different idea? Any group? All lies in one of these. Have anyone not thought about other than these? Okay. So, sorry. Okay. So I want to dig this up a bit more. So when you talk about the limit, so there are common term limit. What you need to talk about the limit? So I think I should make kind of a survey, but raise your hand if you never heard about the term limit in high school. Raise your hand if you never heard about the limit in high school. Okay, everyone knows about the limit, okay? So what do you need to talk about the limit? So let's talk about the limit because it's the common terminology that we all think about. What do we need to talk about the limit? First, we need a function, of course, right? Right? We need something, right? We need something that evaluate the value. What else? Graph. Okay, so graph. And what? So graph is the graph of the function. Okay, so it's a kind of a same thing here. What else? Can we talk about the limit of a function if you only have a graph and a function? Well, you can have a domain. Domain is also information about the function. What was it? What? Range? Oh, range and domain. Yes. Okay, so they're all information about the so these are all like dependent on the function. I think there should be something completely different information, completely independent information than the function. Can I say can I say 1 is the limit of function x squared? Can I say 1 is the limit of x squared? Does that make sense? Why not? Why does it not make sense? Yes, you need a point, right? The point where you want to find the limit. So you need a function and a point. Of course, the function, the point must be on the domain, right? So you need these two type of information, right? So now let's say so we denote that way. So if I want to find the limit at the point 1 or value 1, then you know that 1 is equal to the limit of x squared at 1. And you write this sentence, what I just said, in abbreviated form in a symbol like this, right? But how do you know? That's the next question. How do you convince anyone who see this statement is true? Calculate what? The function at what? How do you calculate the function? Yeah, that's a good way of thinking. So how do you calculate the function? Substitute x by 1. But isn't that just same as 1 is equals to 1 squared? Like you're evaluating the function. So it's a difference equation. So when you take 1 and then substitute the x and then find that it's 1, then you're explaining why 1 is equals to f of x. 1 is equals to f of 1, right? But we're talking about the limit. How do we know this? Okay, so I'm going to give you another 2 minutes to discuss. So yeah, so since Yongjun ruled out that one of possible ways to explain this, which is we can plug in the value, but that should be ruled out because that's explaining different kind of equations. That's not what we want. I mean, this is also true. I'm not saying this is wrong. This is just a different thing. So we want to talk about this. We want to make sure why this equation is true. So I'll give it 2 minutes to discuss how do you make sure how do you check whether this equation is true? You're going to the same group? So the person in the middle is the leader. It should be the leader because you have to discuss to him so that everyone can discuss together. We all learn this. You learn this. I'm pretty sure you learned this. This is not same as plug in the value, right? Teacher should emphasize this, and you should have a problem solved when you that makes you fall into a trap if you try to just plug in the values to find out the limit. So, Choi Bo-sung, it's group 7, yeah. So what did your group discuss? How do you check? Yes. I mean, we're not talking about the continuity. We passed that. So we agree that the continuity is something that involves the limit. So we want to discuss about the limit. But if you go back to the continuity to discuss about the limit, then you're in a circular logic, right? So how about Mushifik, group 17? Uh-huh. Yeah. Okay, so you collect all the information you get about the value of function as you approach x to 1. So for example, you can plug in not 1, but some number very close to 1. So you can start from 1.1. Well, both sides. Okay, so all right. Yeah. So you can go. Yes. Right. So you plug in plug in numbers to find out what this is and see how it goes. Okay. So anyone else have different ideas? So what are you looking for here? So how do you find out this number? Yes, decreasing the range. And okay, so maybe this will be not 1, but very close to 1. Let's say here we get 0, 0, something, something. Here we get 0, 0, 0, 0, something, something. And How do you convince yourself this will be 1, exactly 1 at the end? How do you know? Round it, but it could be not, I mean, if you want to find the exact solution, exact number, it could not be 1, right? It could have a point 0.0000, 1.000, and the 100th place there could be 1, and that could be the exact answer. How do you convince yourself that it's 1 exactly? Right? But there is no other way other than plug in the number very close to 1 to find out the limit. That is the definition. That is the meaning of the limit. You're not plugging 1, just looking at the number near 1 and find whether the value of this function is approaching to. But the question is, how do you know where this value approaches, right? Again, always be careful about the circular logic. You don't want to talk something about, oh, because this function is continuous. No, we want to talk about limit because we want to define the continuity. If you go back to the continuity, the logic is flawed. Okay? So any ideas? How do you know what value should be here?
So 1 is between left meaning and
yes.
Right meaning.
Yes.
1 is equal to.
Yeah, but still, if you plug in the values like this, you can't do it forever. You have to do it finite many times. But every time you only get a shorter and smaller range, but it only gives you the range. So it's only gives the information that your real limit is somewhere in between 9999 and 1.0000 or something here, right? They only give you the range. It doesn't tell you about the exact number of the limit. So here's the catch. Whenever you talk about the limit, it's not the result of computation. It's not the result of computation. It's something that you have to prove, okay? So you can compute the formula. For example, if f of x is x squared, then if you want to find out what f of 1 is, you can just plug in 1 here. So it's just 1 times 1, and you can do arithmetic to find out 1. It's a computation. Limit is not a computation. It's a statement. This thing is a statement, mathematical statement. So you see the difference between formula and statement. Formula is not a statement. In the logical sense, in the big sense, it's a statement. But formula is something that you give that gives a value, or sometimes it gives a statement itself when you plug in some values or statement into the variable. So formula always involves a variable, and it just claims that this is something. It's nothing about true or false. What about statement? Statement, mathematical statement, whatever statement is, it's something that you can determine whether it's true or not. So you have to prove it. So now we are dealing with the proof of the mathematics, and this is the core of the idea of any part of mathematics. So you have to distinguish the statement with the formula. So what does this statement says? It says when you do this, what? You will get f of x closer and closer to 1. Okay? That's the statement. When you make x approaches to 1, then your f of x, which is x squared, will go closer and closer to 1. What do you mean by closer and closer? What do you mean by approach? Okay, so let me write down and then let's have a discussion again. I want to hear from you. So what is the statement here? As we make x approaches to 1, f of x, x squared approaches to 1. Okay, that's what this statement says. How do you prove this? How do you prove this? So I'll give you 2 or 3 minutes to think about, and then just have any chat between your group member to you can do a brainstorming, whatever. Just just spit it out, whatever you think about this thing. Okay? You can ask a question or whatever. So 2 minutes for now. What did you say? What were you saying?
그러니까 저거에 대해서 어떻게 생각하는지 그룹끼리.
Yes. How? Oh, so let me. So the question is, how do we prove the statement here? So we know that this is the statement now. So how do we prove this statement is true? This statement. Okay, so EGU, group 2 EGU, yes. So what did your group thought about? How do we prove this statement? What do you think you should do to prove this statement? Graph, you want to draw a graph. And what do you want to see from the graph? So don't fall to the trap of saying continuity again, because you see, we cannot use the continuity here. All right, so how about Jung Hongyu? Okay, that's the third time, but anyway. Okay. Why do you need epsilon delta? Okay, so, well, he mentioned, he spoiled the fact, he spoiled the fun, but anyway, we're gonna talk about epsilon delta, but I don't want to start from just, this is epsilon delta, remember, or I want to convince you why we need epsilon delta. Okay, so let's go another, Han Seung-yeon, group 11, yes. What did you guys discuss? Yes. Oh, you want to, oh, okay, so so you want to use the fact that when x goes to 1, the limit of x is 1, and you want to say this is 1 square and 1, okay? So now we're going back to the state. How do you know this? Okay. It's okay. And also, and we're going to talk about, I mean, it's in the book, but you need the condition that the function is continuity in order to do this. So, yeah. Well, that's a good try, yes. So, anyone else, any other group who had discussed about this and wants to share? Mm-hmm. Difference between 1 and what? Limit? Limit? But because we want, so the limit is the abbreviation. It's just, it's not a number. It's a statement. It's a, okay, so I think he pointed out the important fact. So as I said, the limit is not a formula, okay? It's a symbol that represents a statement. It says this whole thing is not an equation, because we're not comparing a number and number. We're not just, we are taking this whole thing as a statement saying that as x equals to 0, the x squared goes to 1. Okay? So you have to change your way of thinking that probably have thought about this for a long time in a certain way, but now it's time to change your perspective here. Okay? Because it's really important, because if you if you keep confusing about these small facts, at later you're gonna get lost. So 이편주, group 9, yes. What did you thought about? How did you thought about this? Yes. 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 But that's very convincing data, convincing evidence. So when you keep plug in x 1.001 and 0.00001, and you get x squared getting closer and close to 1 here. All thing, you can't do everything. You can't do all the cases. It's impossible. It's just an evidence. Evidence. Evidence is not a proof. It's mathematics. It's a very convincing idea. It could be possible, but proof means that it's 100% correct. No other exception. But we are getting there. You'll see what we are getting there, how we are getting there. So how do you turn this evidence into a proof? 100% sure. What do we need?
Another two statements.
Another statement?
Yes.
About what?
About, remember, 0.99.
0. Yeah, well, we can do the opposite direction. Yeah, but the same thing. You will get something similar, something very close to 1 from below, right? But it's just convincing evidence. So if you want to turn this evidence into 100% sure, then you need a certain gadget, you need a certain function or a certain whatever, the tool, that if you want to make your x squared as close to 0 as much as you can always find the value x which is even closer to 1 than x squared closer to 1, so that all the values of x squared lies in that region. So for example, here's the graph here. So let's say this is 1 and this is 1. So graph is a nice way of finding evidence whether it's going to be 1 or not, but it's not the proof. But this is just the visualization help to understand what I just said. So I want to see that the value of function is approaching to 1. I can just plug in lots of values, but that's not the proof. What I want is, if I want to get as close as I want to 1 for the function value f of x, so here, if I want to get as close to 1, then I need to know, I want to make sure, I want assurance that if I plug in x in a range very near to 1, so if I have a range of x, very small range around 1, then all the values should lie inside of this small range. I need that assurance, because what happens when I just plug in these numbers? Maybe if I accidentally put the right number at the right point, then this function, let's say, has a different value right above here. So I'm not gonna get a function equals to 1. So think about function as a black box. I don't know about the graph. I don't know anything about it. If I just plug in the numbers like this, I can get an evidence, lots of assurance. But there's always a chance that this function value is jumping up at some point. And if I get that, then I have no idea what's going to be. The only way I can get assurance is that I have a guarantee that no matter how small I take the range of the value at 1, I know how small my x range should be around 1, so that entire value of function lies within that range. That's the proof. If I get that assurance, I know that it's 100% sure that the limit is 1. In fact, that's the meaning of some function or x approaches to 1. We're not actually moving the point because that's the same thing as I'm taking a values close and close to 1. I'm not moving it. I'm looking at the range. And then changing the range, the size of the range is smaller and smaller. So let me put what I just said into a sentence. So if I have a difference between x and 1 really small, that means I take a small value, say delta, and I have all the points satisfying this inequality. It means that I have 1 here in the x-axis, and x lies in 1 minus delta to 1 plus delta. I can pick any value in x. What I want is, if I have chosen small enough delta, then all the functions f of x and at any point in this range fall into small range around 1. So 1 minus epsilon to 1 plus epsilon. So f of x minus 1 is less than epsilon. So now this is the core idea of epsilon delta definition, but there are a little bit more logical statement, logical there's some kind of decorations to make sure that this is the correct statement. But anyway, see what I'm saying? I want to make sure that this value of function lies very close to 1, which means that this difference lies in a certain the difference doesn't go beyond this limit. So epsilon is a very small number, and if in order to do that, I need to make sure that I can choose an even smaller delta that satisfies this. So whenever I have an x in the range of this interval, then I know that the function f of x always lies in here. I need this to prove it. I want you to have a nice feeling about this. I mean, I don't want you to 100% understand why this is necessary, but I want you to have some kind of agreement why it seems right. Okay, so if you have a slightest agreement about this statement, why it's necessary to have this kind of statement to prove the limit, I think you're okay. But now let's go a little bit deeper here. So what kind of delta and epsilon can I choose? So let's say if I fix delta or I fix epsilon, let's say I want to have nice small range, like f of x must be in between 0.9 to 1.1. Is it enough that the limit is 1? No. Well, can I choose this? Is it enough? Or can I choose 10 to the minus 10 power? No, I cannot choose any value, right? I cannot fix this range. I cannot fix this epsilon. So what I want is, I want this for any epsilon, however small it is. For any epsilon, I want this to be true. So in order to make this true, what happens to delta? I need to know how to find the delta, right? So whatever value of epsilon I choose, there must exist, or whatever, however you must exist delta such that if I have a point satisfying this, then the value satisfies this. Then I know that my limit must be 1. That's the way of proving the statement. So let's go a little bit deeper here. Well, if I choose epsilon, well, if I can choose any epsilon, can delta be constant? Can delta be independent to epsilon? If epsilon gets smaller and smaller, delta also must get smaller and smaller. So this delta is not a constant. It's actually a function of epsilon. Okay? So delta is something that you always have to change according to how much you want your value of function close to 1. Okay? So I'm going to prove this in this sense. I shouldn't have erased this, but just remember it. Okay? So let's prove it. So what we need to prove this is we need to know, I'm going to write every sentence here because it's really, really important to understand how the mathematical proof goes. That for every epsilon, which is positive, there must be some delta that is according to the epsilon. So it's not independent to epsilon, it's changing to epsilon, but you can always choose such delta according to epsilon, such that for any x satisfying x minus 1 less than delta, what do we need? The inequality f of x minus 1 is less than epsilon. We need this, okay? So the problem is, how do we choose such delta, even though we don't know what epsilon is, okay? So we cannot, again, I cannot plug in any value to epsilon. It will be just an evidence, okay? So it's not a proof. So what I need is, I need to find some kind of a function of delta in terms of epsilon. So here's how it works. So final inequality, what we want to prove is this. So let's plug in the formula of f. So we want to show f squared minus 1, which is x minus 1 times x plus 1, right? Well, it's obvious arithmetic, is less than epsilon, right? That's our final goal. But we know, all we know is x minus 1 is less than delta, okay? But if x minus 1 is less than delta, then what can we say about x plus 1? So it's a triangle inequality that x plus 1 is x minus 1 plus 2, so you can split and take an absolute value to make an equality like this. So it's less than delta plus 2, right? X plus 1 is less than delta plus 2 when x minus 1 is delta. So this is given. This is our assumption. So we're not still talking about what delta is, but we are assuming what happens when we have this statement, how small this delta should be. So let's combine these two. So in that case, x minus 1 times x plus 1 is less than delta times delta plus 2, right? So if we really want this, what we want is delta plus 2 is less than epsilon. I want this. Can I find such delta? How can I find such delta? If, let's say, delta is minimum between 1 and epsilon over 2, which means that if epsilon is bigger than 2, I can choose 1. If epsilon is less than 2, I can choose epsilon over 2. Just choose whichever is smaller, okay? So that's what it means. Then what can I say? Delta, I think over 3. So this is, so delta is less than 1 because I choose it between minimum among 1 and something. So it should be less than 1. So this is less than 3 delta because delta is less than 1. So and then delta is also chosen between the smaller whatever between 1 and epsilon over 3. So delta is also smaller than epsilon over 3. So 3 delta is less than epsilon, right? So what did I say? What did I show here? So I showed that if I choose delta as this kind of formula, so this is formula, by the way. Okay, it's not given as an arithmetic formula, but it's a formula of a function. It's a function. Then I can show that x squared minus 1, which is split into this, which is less than this, can be always less than epsilon. So I showed here. Right? So it's the end of a proof. That's why x squared is limit to 1. So what's our next destination? So we talked about the limit. What's our next destination? Where did we started? Continuity. How do you define the continuity? Where's my coffee?
Where did you get the
Where did I
formula?
get this formula? By clever judgment, by clever thoughts. So this is just an art. So if this is the art of analysis, you have to think of nice formula. Okay. So the reason why I came up with this is I did a lot. Okay, so I majored in mathematics. I did a lot of exercise like this, so that's why I know it. But I don't expect you to like completely understand and then able to do this kind of proof. But I just want you to at least agree that this is the way we actually understand the limit and how the proof works. Okay, because you don't have to know how to prove, but you can completely understand why it is necessary, why it has to be that way. And I think it's far more important to understand or agree why it should be done. It should have been done that way. So it's like you don't have to be a great painter to appreciate a great paint, right? So same way. So you have to be able to appreciate the definition and the correct definition and the necessity of the proof. But you don't have to be able to prove every mathematical statement in order to do that. So that's what I'm saying here. Any questions?
Can we present
Yes.
this formula in the internet, or you just
There are many other ways of defining delta here. This is not the only way. But I think ChatGPT these days can do this kind of proof easily. So yeah. So you can ask any AI. So I mean, if you're worried about the test, I'm not going to ask you to write down the proof in the test, that kind of thing. Okay. All right. So now, what do we have? Continuity. So let me define continuity because we now know what it means by when I say limit. A function f from one domain to another codomain is called continuous at x in A if the limit p, sorry, so x is a variable. So p in A where x approaches to p, f of x equals to f of p. Okay, that's the definition of continuity. Makes sense, right? If you think about the single variable function, that's exactly what it says. First, you need a value function, f of p. If it's not defined at that point, you cannot talk about continuity. You can probably make a graph or function to be continuous at that point by defining a new value at that point. But by definition, if you don't have a point, don't have a value at that point, you cannot talk about continuity. And you need to satisfy, you need to prove, you need to have this statement as a true statement. That's the meaning of a continuity. And this continuity is not about function only. It's about the function and the point. So when you talk about the continuity rigorously, you need to talk about the continuity of the function at certain point. Okay, you need to talk about continuity of a function at a point. But usually we just say this function is continuous. What do we mean by that? It means that it's continuous at every point in the domain. Usually when we drop the point information, that means it's continuous at every point in the interval or domain. All right, so I want to start from here to talk about continuity or limit of a multivariable function, for example, two-variable function. So I put A, B intentionally that way because I don't want to restrict my function to be single variable function. So let's say, consider A to be a two-dimensional region and B to be the real number. Can I say the same thing here? The two-variable function from two-dimensional region to a real number is continuous at a point. Now the point here is now two-dimensional point, right? So I can draw the graph of a two-dimensional two-variable function as a surface inside of the three-dimension, for example, like this one, x, y, z. And this is the point P in xy plane. And the actual graph is up here. Yeah, so P is two-dimensional. I can say Fp because Fp represents just the value on the z-axis, right? So that's my Fp. What do I mean by the limit of f of x equals to that number? How do you know? How do I prove this? How do I make a statement? How do I write the statement of this thing? So what do we want here? We want that as x. So this sounds like this. So I'll give you one or two possible ways to describe this as a statement. One possible way of describing is, as x approaches to p, the value of function f approaches to f of p. Okay? Let me say it again because it's important. This statement could be read as x approaches to p, f of x approaches to f of p. Now, the second part, when f of x approaches to f of p, makes sense because this is a number. Okay, so let me just make sure that this is two-dimensional region and the value of function is just a real number. So when you have two variable function, this value approaches to this value makes sense because it's the same thing as we discussed in the single variable case. But now when I say x, the two-dimensional point, approaches to a certain two-dimensional point, that may cause some kind of confusion. Because this, you see, here, let me, I can erase this part. So let's say I draw a two-dimensional domain here separately. So this is my, whatever, A, and this is my point. So the same idea that x is not equal to p, we're not plug in x as p, is the same thing. So we are starting from somewhere near p, and we are taking p as close as p. So we are approaching x to p, right? But if you say so, then it somehow indicates there is a path that x approaches to p, right? So when you say x approaches to p, it somehow gives an idea that x is approaching to p in a certain path. So I want to emphasize that this limit is not independent path. It's path independent. What do you mean by that? So this limit is not something that you can compute by trying every path. You don't want to work with the path. I just want to work with whether x is close to p or not. So this, the word approaching has to do something with distance, not the path, okay? So the difference between the limit of a single variable function is that in a single variable case, we only have two paths, two types of paths, right? So that's the left limit and right limit. If you have x-axis here, and this is my 1, to approach 1, there are only two paths coming from the left and right. So you can check these two paths and how about how the function value approaches, and then that's enough to find the limit. But if you're working at the two-dimensional point, here x approaches to p, there are infinitely, imaginably many ways to approach p. So you cannot work with the path to find out the limit, okay? And also the definition is not about the path, it's about the distance. So I'm going to write exactly same epsilon delta statement as I showed you before, but in this sense, what does that mean? So this means for any epsilon, there is delta, so delta is a dependent to epsilon, it's basically a function of epsilon. If the distance between x and p is less than delta, then the distance between f of x and f of p is less than epsilon. That's what this statement says. Where's my well, almost same, except that I use distance. So this is the distance. So this is distance between x and p, and same for here. So if you're working with the value r in R, then this distance is simply the absolute value between absolute value of difference of these two numbers. But as I said, you can also work with any type of function, even when the value of function is n-dimensional point. In that case, what you're looking at is the difference, distance between this point and this point is getting smaller and smaller. Okay? All right, so let's have an exercise. This is something that I'm not expecting you to, completely understand and be able to produce a proof by yourself, but I just want you to have a small agreement about this. So let me change this. So show that f of xy equals to x squared plus y squared is continuous at 0, 0. So which means that this function is continuous f of equals to 0 is exactly written in the symbolic notation that xy 0, 0 f of xy, or I can replace this with x squared plus y squared equals to 0, because the continuity means that the limit is the value of function at 0, which is 0. Okay, I want to show this. Okay, as again, I'm not computing this, I'm proving this statement. How do I prove? Let's look at the statement again. What do I need? I need to find there is such delta that this implication is true. So what is x minus p? So here, this is my x, two-dimensional point. This is my p. What's the distance? It's x squared y squared square root. That is the distance between x, y, and 0, right? So what I have as an assumption in my statement is that it has to be delta. That's given as assumption. And what do I need to prove is this inequality. So I want to show that x squared plus y squared, which is f of xy, the difference between these number and this number is less than epsilon. So I want to find how small my delta should be in order to have this statement true. So whenever I have x comma y satisfying the inequality, I want to have this inequality. So what do I have? So if delta is square root of epsilon, okay, then what? Then if you have x comma y satisfying this inequality, which means that it's less than square root of epsilon, implies x squared plus y squared, or the same thing is here, this is exactly the same as x squared plus y squared, right? Is less than what? Square of delta, which is square of square root of epsilon, which is epsilon. So I proved the epsilon delta statement. So in fact, what I proved is, I proved the statement that when x comma y approaches to 0, the value of function is getting closer and closer to 0. Because I now convinced myself that no matter how I want my f of xy to be close to 0, I can always find how close my point xy should be to the point 0, 0. That's basically the idea of limit. Okay, so I'm gonna finish with this example. A question? Yes.
Where did you get the formula?
This formula? Yes.
The same way?
Because I know that if I put this way, then I can make this inequality true. because this works. But again, this is an art. I mean, there's no one answer how to find such delta.
Whatever will.
Yeah, whatever works, that works. So for example, like again this, right? So if I take delta to be square root of epsilon over 2, then if this is true, then x squared plus y squared is smaller than this. So it's smaller than epsilon over 2, which is smaller than epsilon. So I again show that the inequality is true. You see, so we're gonna graph we're gonna draw the graph of fxy equals x squared plus y squared soon. But the reason why it looks smoothly connected, is because we proved it. I mean, we know that this is continuous function, and so you don't have to prove every function for every point y is continuous, because there are theorems, lots of good theorems that you can just rely on. But let's see. So the theorem. So if f of x, so f and y. So let's say just f and g. So these are function on the same domain to the same codomain, are continuous at point P in A, then so does f plus g, f times g, and f over g. And this one is only when gp is not 0. So sorry, so it's a b should be some real number here. Okay, here. So why is it useful? Okay, so we know that the function p, let's say p, small p, x squared plus x plus 1 is continuous at 0, or let's say y, x, let's make it a two-variable function at point 0, 0, because each of this monomial, this x squared, xy, and plus 1, let's say p1, which is x squared, p2, which is x times y, and p3, which is just constant functions, are continuous at 0, 0. Okay, so if you want to convince why these p1, p2, p3s are continuous, then you can prove it, or you can go further, because in this case, p1, okay, so this is the multiple of x times x. So you can say, oh, why is this function x is continuous at 0, 0? Well, you can prove it. So you can break it down to the simplest function you can think of, and then prove the continuity, and all the function that you can make out of it as arithmetic operation is also continuous. So let's see. Let's prove this one. So what does this statement says? The limit of the two-variable function, whose formula is simply x, is continuous at 0, 0. So this doesn't mean that the function is single variable function, because we are talking about the domain, the point in the domain as two-dimensional points. So it's simply saying that the formula of a function doesn't contain any term containing y. Okay? Or you can say the coefficient of y is 0. So how do we prove this? So again, let me skip all the sentences from now on. What I want is the value of function x, difference with the limit to be less than epsilon. I want this. So want this when we have the distance between x, y with 0 is less than delta. Right? So if we have this, I know that my x, the absolute value of x, must be less than delta, right? Of course, I mean, this one is obviously less than x squared plus y squared, and that is less than delta. So I know that x absolute value is less than delta, and also actually the absolute value of y is less than delta. So if we put delta to be simply epsilon, then what do we have? The absolute value of x, by assumption, is less than epsilon, right? So we know that this function, or this fpx, is continuous at 0, 0, right? Or now let's see, this function is very special function. It's just a polynomial and should be continuous at every point. So what if I just put random arbitrary point instead of 0, 0? Let's try that. So what I want in this case is the limit of this function is equal to the value of function, which is a. So what I want is x minus a to be less than epsilon. And what I have is the distance between xy and ab is less than delta. X minus a squared, y minus b squared is less than delta. So what can I say about this? I know that x minus a and y minus b both are less than delta, right? If I have this. Then if the same delta I put as epsilon, then what I can say this is x minus a is less than epsilon, which is delta. So I can show this, right? So I can choose delta according to epsilon that satisfies this inequality. So therefore, this is true for any x, for any a and b, right? You can do the same thing for y, right? But if you have this kind of inequality, this kind of statement, then you can easily say, because of this theorem, that every polynomial, every kind of polynomial is continuous, right? But polynomial is not the only type of function that we are dealing with. So there are exponential function, cosine, sine, and from now on you can just take it granted that that kind of elementary functions are also continuous. Okay, so it's the proving that kind of elementary functions are continuous, even differentiable in the later. It's not an easy task, and it's not an unimportant task. But if we go deeper in that way, our class should be called analysis, not calculus. All right. So what I want to show you here. Any questions about this before we move on to another, not a little bit different example? All right, I'll give you another example. So if everything is continuous, if everything is smooth, no problem. But problem arises when it's not continuous. What's the case of discontinuity in the single variable function? You can have a discontinuity if you have a different limit for left limit and right limit. You can have a discontinuity if you don't have a point value at that certain point, right? So these are two cases. And what about two variable function? So let's say we have f of xy equals to this, defined as this. So the formula is xy over x squared plus y squared, but that doesn't make sense when xy are both 0. So we define the new value for function when xy is 0. Is it continuous? Is it continuous? Actually not. So we're going to talk about the graph. We're going to see the graph of this function, and we'll see why it's not continuous. See. Okay. So let's draw the graph of that function. So f of f lambda. I think I should use def here. So f, it has input, 2 inputs. I will take a numpy array here, and then outputs the float value, simple float value. And if x equals to 0 and y equals to 0, so I need to have an exception. Then I return 0. Otherwise, I return xy over x squared plus y squared. Okay. Let's draw it. So how do we draw it? The graph of a two variable function? So pi plot as PLT, numpy as, and xx, yy is mesh grid again, linspace. So we are looking at around 0, 0. So let's take -1 to 1 as my range for x and y. And take the axis and plot surface. All right. Forgot the comma. Okay. And oh, I think I should define NP on top. Okay. And oh, okay. So so 0. So how should I deal with the zeros? I'll just put the return here. So it's gonna be none if I plug in 0, 0. It's not going to draw by the plot surface function. So anyway, so this is the graph. So if you want to see the code again, so I'm gonna stay here for a few seconds. So basically the same code I did in the last time. And we're gonna do it a lot for the rest of semesters to visualize anything. Okay, so here's the graph. What does it look like? How does it look like? Well, it looks like there is kind of a canyon here, right? So something weird going on, but it's understandable because when you go near 0 and 0, then it's going to be 0 over 0 somehow. So it's something weird thing should go on. Do you think this is continuous? Can you say this is continuous function at 0, 0? Does it look continuous? Well, it looks continuous, you know? Can you say it's continuous? Can you say it's a continuous graph, continuous surface? So again, as a wrap up of what we learned today about continuity. So continuity is not about what you can see from the graph. It's about how the value of function approaches to certain value. So in order to say this is continuous at 0, 0, we need to convince ourselves that the value of function approaches to a single point, single number as x, y approaches to 0, 0. So what does that mean? No matter which path I take to approach to 0, so let's say 0, 0 is here, I can go 0, 0 in a straight line in every direction. Even this is infinitely many, but I can take any shape, right? I can take any shape to approach it to 0. I can even take the spiral, whatever. It's impossible to think about or classify all types of paths. But if it is continuous, if it approaches the same value, the value of the function doesn't change. The limit of the function value doesn't change no matter which path I take for x, y. So I'm gonna draw a line, three-dimensional line on top of this graph and see what happens. So I'm going to define my C1 as a lambda function. And let's see, this is going to be t, t, one is C1, and C2 is almost same thing, but I'm gonna take 2t, okay? So C1 is just 45-degree angle line, and C2 is a little bit more steeper one. And let's see what happens. So axis plot. So plot simply gives the curve. So here I'm gonna set my t to be the length space from 0 to 1. So the reason, or you can take 1 to 0. So it doesn't matter. You can see decreasing sequence then. And let's see. So when I say C1t, it will give me x and y coordinates, but I need third coordinate for z-axis. So I need f of C1t, right? I think C1t is 0. I think I should do this way. Let me check its work. Okay, so it works. You can see the line up top of this graph, but because it's not transparent, you can't see it clearly. So I'll make a transparency. So you can see that this orange line is the C1 curve. Where does it goes to? So when t equals to 1, it starts from 1, 1. And when t becomes 0, then it goes to 0, 0. But at that point, if x and y follow C1, the value of function approaches to what? Somewhere above 0.4, right? Somewhere on top. So how about C2? Let's draw the same thing with C2 here. So instead of C1, let's change it to C2. Let's see what happens. So the green one is the C2. So where does it land on? So C2 lands on somewhere below than the orange line, right? What does that mean? The limits are different, right? If you take a different path, you get a different limit. Can you say that the limit exists for this two-variable case? No. If the limit exists, it shouldn't be dependent on the path. But if the limit of function depends on the path of the approach of x and y, then it means that it's not. It means that the limit does not exist. I mean, even before we go into the continuity, the limit of function does not exist. Okay? So you can draw a little bit more. So let's say C3 is now, you can work with a straight line, but also you can work with a curve, let's say t square. So it's a parabola, right? T comma t square is a parametric curve of a parabola. And let's see what happens, how it look like. So if I take C3, then you can see that the red line is now curved because it's already curved when you project down onto the xy plane, and follows the surface of the function. But where does it land? It lands on way down below. So it's all limits of these paths are different, right? So no, there's no limit. All right, so that's basically what I wanted about the continuity, and the details on the textbook, but I want you to read more. And also, if I think you probably can think about by yourself. I prefer you to think by yourself rather than going on to kind of mathematical textbooks or some kind of a ChatGPT. Think about what does it mean to have a continuity of a function, especially in the two-dimensional, two-variable case. And what we're going to do tomorrow, next week, is we're going to introduce third topic of the project 1, which is about the contour plot. And it's going to be a little bit complicated. So if you have time, if you need, if you're especially going to do the topic 3 on the project 1, then please read through the chapter 3.3 or 4 before you come to class. So see you on next time.